Today, we're going to continue our discussion of mass spectrometry. So last time, we talked a little bit about what happens during recording of a mass spectrum. First thing we have to do is we have to ionize the sample. There's various ways to do that, but so far we've just talked about electron impact ionization. And once it's ionized, before it might fall apart, then we generate what's called a molecular ion. And for electron impact ionization, this is always a radical cation. Radical cation, and it's always what we call an odd electron ion. Or odd electron ion. Okay? We talked about some rules about kind of identifying this molecular ion and this odd electron ion, which had to do with the nitrogen rule, right? So if there's an even number of nitrogens in the molecule, including 0, then this odd electron ion will have an even mass. And if there's an odd number of nitrogens, it will have an odd mass. Okay? When it fragments, it goes from we'll talk about this today, but if it does a single bond fragment, doesn't rearrange, then it will go from an odd electron ion to an even electron ion. And then the rules are reversed as far as whether the mass is odd or even. Okay. So we're going to talk a little bit more about molecular ion. We're going to go through kind of McLafferty's approach to determining or calculating a molecular formula from the isotopic abundances. We'll talk a little bit about high-resolution mass spectrometry, so a way to directly measure the formula, essentially. And then we're going to start talking about fragmentation reactions. Okay? Okay, so this is where we finished off yesterday, and we kind of read through these steps. So let's just dive into a few examples. Oh, first there's a couple of tables that I put in here, and there may be versions of the similar versions in our text. These come from this old McLafferty text, and so these are pretty good ones to use. So this shows all the different elements, and it shows what type of element he categorizes them. You know, sometimes we use M's, he uses A's, and these are what the significant isotope that's not the, most abundant isotope will be. So, for example, we talked about chlorine and bromine, and he considers these as A+2 isotopes because their most significant other isotope is the +2, right? We talked about how chlorine is roughly a 3-to-1 ratio of this A and A+2. Bromine is roughly 1-to-1. Okay, so the other important ones here, carbon is an A+1 because C13 is the next most important isotope. And we talked about how we could use that to determine the number of carbons in whatever ion we're looking at. Hydrogen can play in a little bit. Oxygen is A+2. It has a little bit of the A+1. So if oxygen 17, but oxygen 18 is a bigger 0.2, and that's enough that we can identify its presence. Silicon, sulfur is a A+2 because it's 4.4%. And so these are, ones that should kind of stand out as we look at this analysis.
When you don't have isotopes, can we detect them or find them?
Yes, because remember, what we've looked at so far is we're actually determining integer value
Or the same.
ions, right? Differences by 1. And isotopes are going to have differences of 1 or 2, and so we can see the different isotopes in the mass spectrum. Okay. All right. So the other table that's kind of good is this one that just shows how the carbon C13 contribution will change for the given number of carbons. And we kind of talked about this, that because it's 1.1% for one carbon, there's a 1.1% chance for every carbon in the molecule
To have C13.
for the C13. And so it just goes up by 1.1. So, 2.2, 3, 4.4 on up. This A plus 2 is how the possibility of 2 C13s in the molecule would increase. And then, in fact, if you start getting up to a lot more carbons, then the chance of having 3 C13s in the molecule starts to increase a little bit too. It's still quite small. Okay?
It's 22.
Huh?
You have 100 carbon atoms.
100 carbon atoms, then the A plus 3 is actually up to 22%. Look at that. A plus 1, 110%.
Which one? Oh,
Over here at 100. Means it's actually higher than the M plus.
why is it? It shouldn't exceed.
Well, yeah, because the chance for every carbon is 1.1. I guess. I've never looked at ones. Well, I think it's rare that you could do EI, but this shouldn't matter what ionization technique you'd use. But once you get up to 100, yeah, then that one gets even bigger, I guess. Down here, they show kind of the same kind of thing for nitrogen and oxygen and silicon and these other ones. These, I guess, came mostly from the other. Well, it just says you add this much. So just like this, so if oxygen for the A plus 2 is 0.2, then if you have 2 of them, it's 0.4. If you have 3, it's 0.6. Okay. All right, so here is our first example. And so here's the rules down here, the steps that we're going to follow. So what we're going to do is we're going to write down just these. We're going to make a table here. So we're going to say M plus 1, M plus 2. And then we're going to write down the isotopic abundances next
For
to
carbon, these M plus?
these are just the ions.
Oh, the ions are.
Right. So the M is the one we're looking at. So here it's at 72. M plus 1 would be 73. M plus 2 would be 74. Okay. Then we're going to write down the abundances. And here our M plus is already at 100%. Okay. And then we have, 3.391 and 0.451.
Why doesn't it show the M plus? It's because of the 100% or?
What are you talking about?
Oh, I see. So the first peak is the M plus.
Yes, so this in our spectrum, this is the M plus.
But that small peak is.
This is M plus 1. This is M plus 2. You can
I
barely,
didn't
it's
see
just a
that.
dot. Yeah, it's only 0.45%. Okay, so then what we're going to do is we're going to follow their rules down here. So we've done this. We wrote these down. We wrote down our M plus. It was already set at 100%, so we don't have to do any normalizing. Now we're going to look for M plus 2 elements, so chlorine, bromine, sulfur, or silicon. And so what we just do is we look at this m plus 2 value, and we look if it's big enough to accommodate one of those m plus 2 or a plus 2 elements, right? And out of those, if it was chlorine, then it would have to be 32%, so that's not, bromine 98%, silicon 3.4%, it's not that big, sulfur 4.4%. Okay, so oxygen is included as an A plus 2 as well, but it's only 0.2, so we're going to wait and we're going to calculate carbons before we calculate oxygen. Okay, so there are no M plus 2 or A plus 2 elements here. Okay, so now we're going to determine the number of carbons. And so we look at this M plus 1 value, and we try to pick how many carbons are in there. In the end, we want to have these all add up to usually be about plus or minus 10%. Okay, so, it's not going to end up just exact here. So, how many do you think we would fit in there? 3, right? Because it's just a little over 3.3, which would be for 3 carbons. So we're going to write in C3, and we're going to write down the values here. The M plus is always 100%, and then this is going to be 3.3, and if you look at the table, then the A plus 2 is 0.4. Okay.
Where do you find this 0.0?
It's from this.
Oh, yeah, I got it.
Yeah, because they all have the A plus 1 and A plus 2. All right, so then we've figured the number of carbons. Now we're going to determine the number of oxygens. So sometimes what we need to do here is then kind of do a subtraction and see what we have left, right? So let's just say the remainder would be, let's see, which one am I doing here? That one, 3.3, 0.091. Oops, that should be for the M plus 1. Let's see, I guess I could probably, oops, no, that's moving the whole thing. 0.091 and 0.411. Okay, so then we look at the M plus 2 peak to determine how many oxygens, because oxygen will contribute 0.2 for each oxygen. So how many oxygens? 2, right? So we're going to write 2. It contributes to the 100% there. And then oxygen, if we look at that first table I gave you, gives 0.04 to the M plus 1 and 0. Oh, but we want to double that. 0.08 and 0.4 to the M plus 2 peak. Okay, so then, we've used up almost everything, and what we have to always be reticent of is we have to add these up, right? So C3, O2, that would be 36 for C3, and 32, that means we've got 868. We're just going to 72. So this has to be C3, O4, no, H4, O2.
How do you calculate the last part, 36 and 32?
Well, I just did 3 times 12
Oh,
for the carbons, 2 times 16 for the oxygens. Right, and then I just took the 72 minus 68, gives us 4, and this is going to be the number of hydrogens. So we fill in whatever's left over with hydrogens.
is it accurate, this method, or?
Well, McLafferty would have said so. But it has these requirements, right, that we talked about before. What were they? We need to have these strong ions with high signal to noise, and we can't have overlapping peaks, right? So for the problems we're going to work, does work well, But if you have a real experimental data, it might get you close. All right. So let's do a couple more. All right. This one. All right. I'm going to see. Well, do I need to write this out? I guess we'll do it. M plus 1, M plus 2, 100, 1.1, 96. I guess we could do M plus 3 then because it's there. 1.1.
1 plus 3.
All right, so first thing we do, look for A plus 2 elements. What do you think? Bromine, right? So that's going to be 100%, and it's going to be, let's see, does it contribute anything to nothing here? 0, and then 98. So that's slightly over, and 0 here. Okay, but that takes up everything except for the carbons. If we want to calculate the number of carbons, just 1, right? Because it's going to be 100 and it's going to be 1.1. And essentially what we have here too is we essentially have kind of like a 1.1 here as well, right? Because we have 1 carbon added to bromine 79, we have 1 added to bromine 81, right? So this is going to be C, and then this adds up to 79 plus 12 is 91, right? So we have CH3Br. All right. Got it? Okay, let's do the next one. M plus 1, M plus 2. And these are at 100%, 0.9, and 5.0. So what do we look for first?
I mean, you look for any N plus 2
Right.
elements.
And what do you think about that?
Thinking that there are some.
Right, because it's
Yeah, but
pretty
it's not
big.
chlorine, bromine.
Right,
It'd be, either sulfur or silicon.
right.
I don't have the table in front of me, but
Oh, yeah, right. Okay, so silicon contributes 3.4, but silicon also has 5.1 in the M plus 1.
so it's not that.
Sulfur contributes 4.4 to the M plus 2 and 0.8 to the M plus 1.
Yeah.
So is that silicon or?
No, because silicon has, you got the table there?
Yeah, it's 0.8.
No, well, silicon has 0.5, now 5.1 is the A plus 1, and 3.4 at the A plus 2.
Oh, sorry, it's sulfur.
Sulfur, 4.4, so we're going to put in a sulfur. 100 here, 4.4 here, and 0.8. Okay?
Yep.
Okay, so next, so we could do the remainder if we want. We're going to have, we'll just put 100, 0.1, and 0.6. Okay, so next,
Why is it 0.1 and 0.6?
I just subtracted.
Subtracting?
Yeah. I was just seeing what's left over, so what we have to account for still.
It's 0.6.
Okay, so the next we'd look for carbons.
Aren't any.
No carbons, right? Because we don't have 1.1 in the M plus 1. So then we're going to look for oxygens, right?
Yeah.
So what do you think?
I think there's 2 of them.
2?
Yeah, that would be my guess.
Oxygen.
So 0.6,
Oh, if it's 0.2, then it'd be 3, right?
it could be 3, that value, but can we, does
0.1 doesn't work.
that fit though?
No.
Right, because we're only going to add to 64, right? So 3 would be too many.
Yeah.
Right, so we just got to go with what we can fit in there. So we're going to fit O2. This is 100. And let's see, for oxygen, it was 0.08 and 0.4. Okay.
I think so.
Huh?
All right, yeah.
And the rest with
And then it just adds up to 64.
hydrogen?
There are no hydrogens.
No hydrogen?
Right? Because one sulfur is 32 and 2 oxygens is 32, so we've added up to 64. So this is just for SO2. Right?
I was right beforehand.
You were right, but
I know, you got to go through the process, yeah.
right. And yeah, maybe you could have jumped to there if you would have just, calculated what masses we needed to left.
Yeah, and the fat, yeah.
All right, so let's do one more. And this one we'll do 2 different ions in this one. Okay, so let's start out with the molecular ion. Okay, so we look down here on our big table. 154 is the molecular ion. So M plus 1, M plus 2. Here, I'm going to write down the ions we're doing too. It's 154, 155, 156. There is one at 157, but I don't think we have to worry about it. Okay, and now this one is the base peak, so 109.8 and 5.1. Okay, so we look for M plus 2. It has a...
Why we don't work with the 157?
Well, just because that would be the M plus 3, and we don't really have much of a contribution to that, unless we have really a lot of carbons that we can calculate. But, if we have an A plus or M plus 2 element, then that would have some C13 attached to it as well, right? But I think it's more complicated to calculate that than we need to, right? We'd have to normalize that up to 100% and then see what the C13 contribution would be. All right? So what do we think?
It's
Is it silicon?
well,
It could be, but I think what we want to do is, both silicon and, sulfur have that A plus 2, but silicon is 3.4 and sulfur is 4.4. So we
sulfur.
yeah, we probably want to try to account for as much of that peak as we can. So
we should start with the closest values.
Yeah, I think
The
so.
element.
Yeah. So I think we should add in a sulfur. Okay, so 100, and this was 0.8
Yep.
and 4.4, right? Okay, so let's look at what we have left over. Oops, it can't fit in there. Okay, remainder.
1
We have 9.0 and 0.7.
What was the second value? 1 point. The second row after 1 between points.
9.0.
Oh, no.
Yeah, because all I'm doing here is just subtracting 0.8 from 9.8 and 4.4 from 5.1. All right, so then what do we think? We're going to put in carbons, right? So how many carbons?
Why carbon? Can you fit any other elements? Or?
Well, we're just following the rules. If you want to break the McLafferty rules, then I'm going to really get on you here. 8, right? Most likely. So this is going to be 100, 8.8, and for 8, 0.18. No, 0.34. All right. So then we might want to figure out both what we have left over and maybe what we how much mass we have left over too.
0.2.
Okay, so we have C8 and we have 1 sulfur. I don't know if I have down what that adds up to. But I did put in here, I'm going to have to curve this thing down. I wonder, can't I?
128.
128? Okay, so this is 128. And then let's say what we have remaining over here. I kind of crunched myself here. I thought there'd be a way that I could... Oh, maybe I can do that. Move, oops. Oh, shoot, I erased that.
128.
This is 154, 155. Okay, and then remaining, we're going to have 0.2 and 0.36. Right, because I just subtracted 8.8 from 9 and 0.34 from 0.7. Okay, so what do you think we have? What else?
We might have
an oxygen. So that was 0.04. No, 0. And 0.2. Okay, so let's add these up. C here and oxygen.
How many oxygen? Just one?
Just, well, I think just 1. We could maybe fit 2 in there, but mass-wise, I think that this adds up to 144. And so we only have 10 mass units left over, right? So that means that we have to have H10. 10. So 154 minus this is 10, and this is going to be the number of H's. So C8H10OS. All right. All right, let's do it for the peak at 139.
So what's the difference between these? Is it just one molecule or two molecules, these ones?
What do you mean?
The 139 group.
No, those are, so this is the M plus, and these other ones are all fragment ions.
Okay.
Right, we're assuming, we don't just have a mixture of compounds that we're analyzing.
Just one.
Right. And notice that this is an even mass, right? We had an even number of nitrogens. 139 is an odd mass, right? So if this is an odd electron ion, this is going to be an even electron ion, right? So it's a fragment ion. But we can do the same thing. So we're going to do 139, 140, 141. This is going to be our M plus now, M plus 1, M plus 2. All right, and we're going to write these in. Let's see here, 139 right here, 32, 2.7, and 1.6. Okay, so now what we have to do, because this isn't the base peak, we have to normalize this up to 100%, right? So we just take 100 divided by 32, and we get whatever value that is, and then we multiply that by 2.7 and 1.6 to get the other ones, right? So we want to go up to 100% here, and if we normalize it, this is our normalized one, then we get 8.44 and 5.0. All right, now we're set. We want to do the same process. Right? So what sulfur again?
Yeah, sulfur again.
Right? So this is 100, 0.8, 4.4. So we're going to have like 7.64 or something like that, right?
Yeah.
So how many carbons do you think?
5, 6.
Okay, we can try that. See, 6 would be 100, 6.6, and let me look back here, 6.6 is 0.18. Okay, and then what?
Look at oxygens.
Oxygens?
That's not right.
6.6.
So we'd have to do our subtractions here. So 8.44 minus 0.8 minus 6.6. Remaining. I don't have a calculator.
1.04 for 140 and 0.42
1.04
for 141.
and what? 0.42.
42. Wait, yeah. Did I just do the math wrong? No, I'm good. I'm good.
So what kind of mass do we have left? So 6 times 12 is 72, right? And plus 16, we're only up to 88. No, this is 32. Oops. 32 for 104.
It's not enough carbons. Because if you go down the route, like you can only have one max oxygen, so that would give you a mass.
Right, because this looks like we have 2 oxygens, right? But we can't end up with more oxygens in a fragment ion than we did in the starting one. So, right. So I think probably instead of C6, we're going to go to C7. So this is 100 and 7.7 and 0.25. All right, and if we have 7 times 12, well, then we 0.25. So then what's left over, this mine is getting too messy here. This other time I ended up with enough space to write all this in there. We didn't do that, so
140 is negative 0.06. And then
what is?
It's negative 0.06.
Negative 0.06. This is remaining.
And then 141 is 0.35.
0.35.
The negative remaining is fine, or?
Well, remember we're trying to get plus or minus 10%.
10%.
And
So it can be slightly over or slightly less. So it's basically the amount of experimental error in there.
0.06 is probably okay.
Yeah. Oh, yeah. That's a 0. Yeah. So that's that's pretty close.
Yep.
Okay. So what else do we got to put in here then?
Probably an oxygen.
Probably an oxygen, right? So this would be 0.2, 0.04. All right. So then we end up with C7, H. We have an oxygen, and we still have our sulfur. And all of that I guess adds, I don't know what I was, oh, that's what I was doing there. So I think we end up with 7 hydrogens. Just as a remainder, basically. So does this make sense?
Not particularly, because that's an unusual fragment.
Is
Or
it?
an uncommon fragment, that's what it was.
Well, let's look at the difference between here. What have we lost?
Lost 3 hydrogens.
And?
2 carbons.
No.
Oh, and a carbon.
And a carbon.
So it's a methyl.
Minus CH3. An unusual fragment.
Yeah, it's definitely.
So the other way we could, get this is we're going from 154 to 139, and this is minus 15, right? Which would mean minus a methyl group.
Obviously.
Why it's not a common fragment to lose CH3 this month?
Well, a methyl group is anything, there's going to be methyl groups on the periphery of different molecules, and so those are common groups that you could lose.
So it's common.
Yeah, sure.
Okay, I thought maybe you said it's uncommon.
Well,
I said
that's what Andrew said before he fully thought it out.
before I saw that carbon loss.
Yeah. Right. If it was just a loss of H3, then that would be uncommon. But, a methyl group is a common group in organic chemistry, so that's an easy one to lose. Okay, so, if you were doing this, you could go down and continue and do these for these other, ions. I'm not sure. There's a lot of kind of small things here. I don't know how much those might, if you have some overlapping peaks in there or not. even this one, oops, even right here, notice there's a little peak here, which would contribute a little bit, to the, because it has a n+1 as well and stuff. So, but we'll just stop here. So you could this is basically the process, for any of the peaks, whether it's the molecular ion or a fragment ion, if it's not the base peak, then you have to normalize it to 100%, and then you just go through this same process. Okay? All right, so let's move on here. So the other way was probably more common to try to come up with a molecular formula is to use high-resolution mass spectrometry. So in this way, you can actually, if you can measure the mass out to like 4 decimal places, you can oftentimes come up with a mass that matches a specific molecular formula. And the reason that you could do this is that if we look at the masses of individual isotopes, they're not actually unit masses like we've been using. So, for example, hydrogen, well, we got to make a point here, too, that for hydrogen, the actual atomic weight, if we look at the periodic table, the atomic weight is 1.0794, right? And we have to make sure we can't use this weight when we're doing mass spectrometry. Do you know why?
Isotopes?
Right, because of the isotopes, and this value here is just a weighted average. Yep. All isotopes. Okay, and so over here on the right side are the actual masses. Okay, so for a proton, the mass is 1.00783. For deuterium, it's 2.0141. And the atomic weight is the weighted average that takes into account the natural abundances. Right? For carbon, the atomic weight in the periodic table is this, but the actual masses of the isotopes, actually, I think carbon is set and everything else is measured relative to this, that carbon is 12.00000, C13 is 13.00336, right? It's not just exactly 13. Nitrogen has its isotopes, oxygen, O16, O17, and O18. One thing that's interesting is that notice that for oxygen, I think it's the only one that actually has the weighted average of the atomic weight, which is less than the unit weight that we use, right? Oh. Right, so the isotopes are all slightly less than the unit value. Okay, so the point is here is because all of these are not exactly a unit mass, that if we pick a unit mass, like if we pick something like 138, there's actually a whole bunch of different molecular formulas that can be in the 138s. Okay?
But there are 4 remaining digits are different.
Right. Exactly. And, well, what I didn't say is these these slight differences from unit masses are called the mass defect. So that's the difference from the unit mass. So notice as we go down here, 138.06, 0.03, 0.05, 0.01, on down. And so what we could do is if we can measure, I thought that was 6. Yeah. If we can measure the mass of our ion accurately enough, So let's say we measured this to be measured to 138.0321. Okay, so let's go. There's actually programs that you can use. So let me switch over and see if we can find. Let's wake this guy. Oh, yeah. All right, we're gonna go. Maybe we don't. Oh, maybe I can do that. Oh, I think I can do this on the. Just a second. Let me look on here to see if I still have it. But that's, how you do that usually. And usually what they're doing, I think, is they have some standard that they put into the sample. They run at the same time or back to back or something that they know the mass of, and then they do a ratio to calculate the mass of the ion that you're looking at, that you're interested in. Okay? All right. So the next thing we want to look at is the fragment ions. Okay, so we've talked about the molecular ion mostly so far. So we want to talk about fragment ions, and we're going to look at a number of different cleavage mechanisms. All right, so we'll start with the main ones, and then we'll see a few other ones as we go through. There's lots of different ones, but we're not going to look at every possibility. Okay, so the first thing we need to know before we talk about fragmentations is for a given molecule, where's the likely place, and we talked about this a little bit already, where's the likely place that the molecule is going to ionize? Because if we're going to draw a mechanism, we have to know where the charge or the radical are. Okay, so most commonly, so the ionization preference. And I think this just has to do with the ionization potential of the different electrons in the molecule is usually going to be non-bonding electrons is going to be more than pi electrons and more than sigma electrons. Okay, so the first one we're going to look at here is called a sigma cleavage. So this is from a sigma bond, and because that's the least likely to be ionized, this is going to be most common when there aren't other functional groups, for alkanes and things like this. And we kind of talked about this a little bit. In this case, if we have just some alkane like this with a sigma bond, we ionize it, we shoot it with electrons, we form our molecular ion, right? So this would be our molecular ion, and it's an odd electron ion. And essentially, we've just weakened that bond, and so this can cleave in two different ways. The left R group could be the radical, and the R prime could be the cation, right? And notice this cation that's generated is an even electron ion. Or it could fragment in the other direction. So the R is the plus, and the R prime is the radical. Okay, and remember when we run the spectrum, all we will observe is the cations. We don't observe the radicals. They just get pumped out into the vacuum pump. All right, and we often see the loss of the larger radical. Unless, well, what we usually see is the most stable cation is formed. But if we have two cations of equal stability, then we see the loss of the larger radical. If equal stability, loss of larger radical.
What a little larger radical?
I don't know why, but that's just the empirical observation.
It goes out from the instrument, or?
Yeah, the radicals, they just, because remember in EI, we're doing this under high vacuum. We have a vacuum pump that's pumping it out. So anything that we don't observe, there can be other things formed. We could have anions that are formed in the process or neutral species. Any of those will just be pumped out.
With the neutral species?
Yeah, and only the cations get accelerated down this flight tube and down the...
And the smaller ones, probably.
Well, all of the cations will be accelerated and will be...
But if they have equal stability?
Well, these will all be observed. I'm just saying if they're equal stability and we see more of the loss of the larger radical, but remember, these are all just competitive mechanisms taking place at the same time. Right? Like we'll look at some more spectra, but like we saw before when we had an alkane, we see, a bunch of different peaks, but we didn't see a lot at high mass. So we didn't see, if we had a decane, we didn't see a lot of loss of methyl group. We saw more cleavages in the middle and losses of more abundant ones where we lost a bigger radical. Right? But it's all competitive, and so we'll see a whole bunch of different ions, right? We don't just see a single one. Right? Okay. All right. So the next one is called a homolytic cleavage. And so based upon that name, homolytic, this is, homolytic is when we cleave a bond evenly. I guess we can draw these down here. So if we had something like this, so if we had a homolytic bond cleavage, means we're going to cleave the bond with an equitable or even splitting of the electrons, right? So this would give us two radicals. If we have a heterolytic cleavage, then we have an unequal splitting of the electrons, and we would end up with one of these with both electrons and the other one with none of the electrons. Okay? So homolytic cleavage is usually going to be a radical induced mechanism. And this one is oftentimes referred to as an alpha cleavage. All right, so typically this is going to happen when we have non-bonding electrons or pi electrons. Okay, so let's look at a situation here. So I'm just going to put a Y group here. It's going to have non-bonding electrons on it. It could be oxygen, nitrogen, sulfur, different groups like this. Okay, so we're going to shoot it with electrons. We talked about if we have these possibilities, then the non-bonding electron is going to be where the ionization takes place rather than sigma bonds, like we saw up above. So we get this Y with a plus and a radical like this. So this is the molecular ion. And notice because it has an unpaired electron, this is our odd electron ion. Okay, so the radical-induced mechanism is going to take this radical. Remember, when we draw radical mechanisms, then we use a single-sided arrow showing the movement of a single electron. So that electron is going to go down here, and it's going to combine with one of the electrons from this other sigma bond. And that bond is going to homolytically cleave. All right, so this bond right here, one electron is going to go to the left, one electron is going to go to the right. Okay? And what we get out of that is that we have this R to Y. We're going to have a double bond over here now. Still has a plus charge on it. And we're going to lose this R prime radical. So I think the idea is that this would be the alpha carbon, and we're cleaving just on the other side of the alpha position. Right, so that's why it's called an alpha cleavage. Okay, and notice that like before, this is an even electron ion, and we're losing this neutral radical. All right, so we could, well, we'll show other examples later, but this could also be done if we had, say, a pi bond. When we ionize it, the way we draw this is that we can draw, so in this pi bond, there were two electrons over there, and now we've lost one of them. So we have a plus. We could draw them together, or usually we draw them a plus on one side and the radical on the other, but we could do it either way. Yeah. Okay, but once we have this radical, we can do this alpha cleavage. So this radical goes here, combines with one from over here, and we do the homolytic cleavage of that bond. So what we would get is this plus this. And so notice what we're generating here is this allylic cation. Right? So that cation is stabilized by resonance, and this is also the even electron ion. And if it's just some double bond in a chain, it could cleave the other direction as well. All right, so we'll look at more examples as we go, but let's look at this other one, the heterolytic cleavage. This is going to be a cation-induced mechanism. So from this radical cation, instead of showing a mechanism that uses the radical, we're going to have a mechanism that uses the cation. Okay, so these are commonly like this. So we could have this same kind of group that we did before, oxygen or nitrogen or something like that. We're going to ionize it. Electrons. We're going to generate our molecular ion. I'm going to draw the plus on this side now. Prime. And in this case, what it does is it cleaves the bond that's directly attached to the heteroatom. And it's going to move a pair of electrons, so it's going to be a double-sided arrow, and those electrons are going to go towards the plus. And so if that takes place, then we end up with Y. We have a radical here. We got that pair of electrons. So this is a neutral radical plus. The plus is going to be on the alkyl side this time. Okay, so the cation's not going with that heteroatom. So here's our even electron ion over here. So odd electron ion. All right. All right, so the next one is going to be some rearrangements, but I think since it's almost time, let's just pick those up next time. Okay? And then once we finish those rearrangements, then we'll look at a few kind of general rules, and then we'll start just kind of going through different functional groups and looking at how those functional groups cleave. And then we can get to unknowns.